In this semester of chemistry, you'll likely be learning about carboxylic acid, its derivatives, and the concept of nucleophilic acyl substitution. This video will do a quick review of the basics of nucleophilic acyl substitution, and then we'll branch off into the derivatives of carboxylic acid, two of which I've listed here, ketone and acyl anhydride. If this is what your relationship with carbonyls are right now, have no fear. With enough time and practice, you'll be conquering over carboxylic acids like this in no time. For a quick review of the basics, let's do an easy problem. If you need more help with this, I highly recommend Khan Academy. They have many really good videos on these subjects. So this problem was grabbed from worksheet 14/15 of spring 2018 for Chem 202. So here we have an acid chloride and a hydroxide as our reactants. So what will end up happening is that this hydroxide will come in here, knocking up this electron pair to right here. Now that will cause this oxygen to have a negative charge, but this oxygen doesn't want to keep that negative charge, so what it will do is it'll knock back an electron pair here. And we have two options. We have this Cl leaving group, or we have this OH leaving group. Now this Cl leaving group is actually a better leaving group. So because Cl is a better leaving group, we will get this electron pair back onto the Cl, and our products will be a carboxylic acid and a chlorine ion. So that's the basic idea of what this concept is. Now let's dive into some deeper problems, ones that might be a little bit more confusing. So here's the main problem I wanted to focus on. Looks intimidating, no? It's from the third exam of spring 2018 Chem 202, and it caught me off guard big time. But the key to solving these problems is to not be overwhelmed and to simplify it to something that looks more familiar. So in this problem, we can imagine this region where we will be doing our substitution to look more like this. And when we see this compared to these two rings right here, this makes it so much more simple. Now we kind of understand what we need to do. So now let's start doing our substitutions. First, we protonate this double bonded oxygen with the H3O plus that is in the solution. Next, this causes this water to come in and kick this electron pair up. So it causes this water to come in and kick this electron pair right up to this oxygen. So now this oxygen and this carbon don't have any charge on them, but this oxygen now does. So what will happen is that another water will come in and take that hydrogen, and this bond will pop back onto this oxygen. So up to this point, everything has been pretty standard. This is all stuff that we've seen. But now it looks very confusing. If we were to imagine this as a regular problem, however, we'd understand that this oxygen would grab an H from the acid around it because it is an electrophile here. The way that we can imagine this is just by simply imagining it as this problem. Here, this would be the ideal leaving group. So we do the same thing here. So now this oxygen has grabbed this H, which gives it an overall positive charge. So now to get rid of this, we knock down this electron pair right here, which then in turn, because now we have too many bonds on this carbon, we knock this right onto the oxygen. So now we get something that looks like this, with this oxygen having a positive charge yet again. So what is the way that we can get rid of that? Well, we can have another water come in and grab this hydrogen off, pushing that back down onto the oxygen, and we end up with that as our final product, along with our H3O plus. So the key thing to take away from all of this is that when you're feeling overwhelmed through these tougher looking problems, remember that breaking it down into something you recognize is essential. So, we just turn this 2-ring monster into a piece of cake. Thank you.